Hello everyone. In this lecture, we will discuss the eigenvalues and eigenvectors of a matrix. What is called the spectral theory or eigenvalue problem. So, as far as this application of this eigenvalue and eigenvectors or the spectral theory is concerned, it is one of the most important topic, one of the most important aspects in linear algebra. It has wide applications. Specifically, you find its application in quantum mechanics, in vibration theory, coming to the mechanical engineering, in vibration theory, in stability equilibria, in chemical kinematics. Also, if you solve a system of differential equations where we need the help of the eigenvalue. So, eigenvalue problem is one of the most important topic of your linear algebra. So, to have a deep knowledge of eigenvalues, you should refer to my earlier two lectures, initial lectures, that is my Gauss elimination, and the second one is my rank of the matrix, where the some basic thing of your elementary row operation, how it is used to reduce the matrix. So, this technique will be helpful in solving the eigenvalue problems. Okay, so you must refer to my first two lectures. One is the Gauss elimination method and another is the rank, to have a better understanding of this chapter. So, if I think of, I will discuss here this eigenvalue problem in the sense of a matrix, right? Means you are given a square matrix A. You are given a square matrix A, right? Now, X is a non-zero vector. If A multiplied with X, column vector, is same thing as some constant, some scalar lambda is multiplied with X, right? Some scalar lambda multiplied with X. You see, left hand side A is a square matrix. A is a square matrix, right? And what happens to lambda? Lambda is a scalar, right? Lambda is a scalar. Now you see, so a matrix multiplied with a vector in left hand side, in right hand side a scalar multiplied with the vectors. So it is surprised to see the left hand side is same as the right hand side. The moment x is equal to 0, or you can say that yes, 0 is equal to 0 is alright. But here we are discussing the case when x is not equal to 0, right? You see, is it not interesting? X is not equal to 0 and left hand side a matrix is multiplied with x. In right hand side a scalar is multiplied with x. Okay, it is surprised to see the left hand side is same as the right hand side with x not equal to 0. And after simplification, if you solve it, the value of lambda is called the eigenvalue, right? So now if I think of the definition, a square matrix, A is a square matrix, okay? A is a square matrix. Note that it must be a square matrix, right? And lambda is a scalar. A lambda is a scalar. This scalar may be real or complex. Okay? And this lambda is said to be a eigenvalue of A. If there exists a non-zero vector x, x must be not equal to 0 such that this equality holds. A into x is lambda into x. So this is the basis of your eigenvalue. Now the real definition in advanced mathematics, we see the real definition of eigenvalue problem in the sense of a linear operator, right? Let me to tell you in the sense of the linear operator. Let T be a linear operator. Let T be a linear operator on a vector space, right? On a vector space. Vector space, already there is a lecture on vector space where we define two compositions, internal composition and internal operation and external operation, and satisfying 10 properties. Okay, you can refer to my vector space lecture. So now in place of T we have a vector, we have a matrix A. Okay, here we replace T by A, right? Let T be a linear operator on a vector space V over F. A scalar lambda is said to be an eigenvalue of the operator T. if there exists a non-zero vector x in V, right? V is the vector space, and x must be not equal to 0, non-zero, such that t of x, okay, is lambda x. Then this lambda is said to be the eigenvalue of the linear operator t, right? As we correlated that lambda to be the eigenvalue of the matrix A. Now corresponding to, if you simplify it, we'll find the values of lambda. We'll find the values of lambda is lambda 1, lambda 2, so on lambda n, and it is same as the order of the matrix. If A is having the order n cross n, then we will get the n number of eigenvalues. Okay, then corresponding to each eigenvalue we have a eigenvector. For lambda I, we must have a, it corresponds to a vector xi which is not equal to 0, right? And that has to satisfy this relation. This individual lambda I corresponds to an eigenvector, and it has to satisfy Ax is equal to lambda x. So without much delay, let us discuss the details of this eigenvalue problem with several illustrative examples. So let us first see how to find the eigenvalue. You are given Ax is equal to lambda x. We need okay, x is not equal to 0, right? So is it not the same thing as I into x? I is the identity matrix, where I is the identity matrix. No harm to multiply the identity matrix. Then bringing this to left hand side, here A minus lambda into I into x is equal to 0, right? Is it not a system of linear equations? Is it not of the form Ax is equal to B, right? So now this is a system of linear equations, and it is a homogeneous system. Right? It is a homogeneous system. Ax is equal to B, B is 0 here. It is a homogeneous system. And you know, the homogeneous system is always consistent. Because xi is equal to 0 for all I. At least one solution. At least one trivial solution. But we are interested in obtaining non-trivial solution. Xi obtaining non-trivial solution. That means at least one xi is not equal to 0. We are interested in non-trivial solution, and for which, what is the necessity? For this non-trivial solution, to get this non-trivial solution, the necessity is this A minus lambda I determinant is not equal to 0. This non-trivial solution exists only when so this is equal to 0. This A minus lambda I determinant is equal to 0. Okay, and this is called the characteristic equation. This is called the characteristic equation, which is called the characteristic equation. Now simply determinant of A minus lambda I, this is called here characteristic polynomial, right? Now if it is equated to 0, then it is called the characteristic equation, right? So let us now see what is the working rule to find the eigenvalues. The other names of eigenvalue, also called the characteristic root, or the latent root, or the eigen root, or the spectrum. Okay, spectrum, that's why it's called the spectral theory. And what is a spectral radius, right? It is the, suppose you are getting, solving a third order matrix, you are getting, suppose lambda is 3 minus 7 and 5. Then you take the absolute value of, what is the maximum of modulus of 3 minus 7 modulus and 5 modulus. You see, Now this minus 7 modulus is plus 7. So this is 3, 7 and 5. And the maximum value is 7 here. So the spectral radius is largest absolute value of the eigenvalue. So I write it. This is for modulus, absolute value. And the largest, the maximum one. Okay. So this is the spectral radius. Now let us see the working rule. Now consider the working rule. Consider the given matrix. Consider the given square matrix A. Next, write the characteristic equation. Determinant of A minus lambda I is equal to 0 and solve it to find eigenvalues lambda is equal to lambda 1, lambda 2, lambda n, which is, if A is having the order n cross n, then we are getting n number of eigenvalues. Okay, so these are the eigenvalues. Then corresponding to each eigenvalue, there exists an eigenvector. In particular, for lambda is equal to lambda I, right? There exists xi not equal to 0, such that A minus lambda I into xi is equal to 0. Okay, for all I, it will be repeated for I is equal to 1, 2, 3 and so on up to n. Then we'll solve it to get the value of xi. We'll get the value of xi, x1, x2, some xn, like that we'll get it. Okay, now this is a eigenvector, right? This is a eigenvector, and this must be not equal to 0, non-zero vector. At least one of this xi is not equal to 0. Now you note that any scalar multiple of, you note that if xi is a eigenvalue, so also kxi is also an eigenvalue, eigenvalue, right? K is not equal to 0. That means to say and any scalar multiple, non-zero scalar of an eigenvector is also an eigenvector. Okay, so let us solve an example, then your idea will clear. So you are given a square matrix of order 3 and you are asked to find the eigenvalues and eigenvectors. Consider the characteristic equation. Determinant of A minus lambda I is equal to 0. What does it mean? It means here 8 minus 6 minus 3 minus 6 7 minus 4 2 minus 4 3. This is your A minus lambda times same order identity matrix 1 0 0 0 1 0 0 0 1. Since it is 3 cross 3, we are considering this, and this determinant is equal to 0. Okay, this determinant is equal to 0 means this is my lambda, this is my lambda, and this is my lambda. So here only in place of this diagonal, this lambda will be just subtracted, is not it? Here only. So that means here 8 minus lambda minus 6 minus 3 minus 6 7 minus lambda, is not it? Here lambda minus 4 and here 2 minus 4 3 minus lambda. This determinant is equal to 0. You may write it directly. You write it directly. Okay, this is equal to 0. Now we have to solve it. Now. So this implies here lambda is equal to 0, or here lambda square minus 18 lambda plus 45 is equal to 0. You have the middle term factorization. You see this 18, 15 and 3. Okay, so middle term factorization. So this implies lambda is equal to 0, or lambda square minus 3 lambda minus 3 lambda minus 15 lambda plus 45 equal to 0. Okay, plus 45 is equal to 0. 45, you see, minus 3 minus 15 is 18, minus 18, and their multiplication is 45. This is middle term factorization. So this implies here lambda is equal to 0, or lambda into lambda minus 3 minus 15 into lambda minus 3 is equal to 0. So that means lambda is equal to 0, or lambda minus 15 into lambda minus 3 is equal to 0. So that means lambda is equal to 0, and this is here 3 and this is here 15. Okay, so there is a confirmation test whether it is true or not. There is a confirmation test to see whether this is true or not. If you add them, okay, if you add them, this is 0 plus 3 plus 15, it is 18, and it must be the trace of the matrix. The trace of the matrix is if you add this diagonal element. Okay, this is 18, 8 plus 7, 15 plus 3, 18. So here if you add all this, it is the trace of the matrix, given matrix. That means here lambda 1 plus lambda 2, if you all eigenvalues, and this trace of the matrix means all the diagonal element a11 plus a12 plus a1n. This is called the ann. Okay, summation aii, and this is your summation of lambda I, and this is one property, right? Sum of the eigenvalue is equal to trace. And here another property is if you multiply lambda 1 into lambda 2, if you multiply them, right, this will give determinant of the matrix, right? That means in short we write it, this is the multiplication symbol, product of all eigenvalues lambda 1 lambda I means lambda 1 into lambda 2, so on lambda n is nothing but my determinant of A. This is one of the beautiful property, right, to correlate the eigenvalues with the matrix. Okay, now corresponding to each eigenvalue we have a eigenvector. So since the order of the matrix was 3, we got 3, it's fine. Now we will get 3 values corresponding to 0 we have eigenvalue, similarly for 3 and similarly for 15. So for lambda is equal to 0, let x is equal to x1, x2, x3, right? Or we may write it x1, x2, x3 transpose. In order to write in a line, you may write like this or this. Let this be an eigenvector such that a minus 0i into x is equal to 0. So you see here lambda will be replaced by 0 here. Here lambda will be replaced by 0 here, and this determinant sign will be replaced by your matrix sign. Okay, so that means here the matrix here is 8, so it is 8 minus 0 minus 6, 2 minus 6, 7 minus 0 and minus 4, and here it is 2 minus 4, 3 minus 0. Okay, no change, and you see this is matrix sign. Okay, x1, x2, x3 is equal to here 0, 0 and 0, right? If you solve it, it is a system of equation now, is not it? It is a system of linear equation. Is it not of the form a into x is equal to 0? It is a homogeneous system. Right? And we will solve it. So this implies my 8 minus 6 and 2 minus 6, 7 and minus 4, 2 minus 4 and 3. Okay, x1, x2, x3 x3 is equal to 0, 0, 0. You see, so if I think of a augmented matrix, if I think of the augmented matrix A together with X, okay, so this is my A, this is my A, this is my A together with B, this is my b. So there will be no change in b, because b is all elements are 0. Any operation will lead it to the same thing. So here we want to adopt, suppose I have already told you the Gauss elimination technique. I have already told in my lecture 1. So I want to solve the value of x1, x2, x3, means using this I want to bring this 0. So let me to replace r1 and r3. If I replace it, and the remaining thing is same here, is my 0, 0, 0. So I replace r1 is replaced by r3 for easy calculation. So it will be my 2 minus 6 2 minus 4 3, and this middle row remains silent, minus 6 7 minus 4, and it is my 8 minus 6 and 2. Okay, now I use this to bring this thing 0. So it is 2, it is 6. If I multiply 3 here, it becomes 6, and I add row 1 and row 2. So what I have to do is, here r2 is replaced by r2 plus 3r1. At the same time, if I multiply 4 in r1, it becomes 8. So 4 times r1 is subtracted from r3. r3 is replaced by r3 minus 4 times r1. So after simplification I will get, so if I solve it, now my first row remains silent, 2 minus 4 3, and here it will 0, here it will 0, and if I simplify it, it will be my minus 5, it will be my plus 5, it will be my 10, it will be my minus 10. Okay, then next job is use this to bring this 0. Okay, if I multiply 2 in row 2, then what I have to do is, row 3 is replaced by row 3 plus 2 times row 2. If 2 is multiplied with row 2, right, and added, then this will vanish. So this is 2 minus 4 3, and 0 minus 5 and 5, and it is 0 0 and 0, and this remains same, x1 x2 x3, and any operation, this operation will also give you the same thing. If this operation is applied here, no right hand side is not going to be changed here. So this, okay, now we are ready to solve it. You are ready to solve it, and you must note that you must get, if the eigenvalue is repeated, is distinct, only occurred once, then we must have one independent row. So always you see, this simplification will give you 1 0 row. Okay, because lambda is equal to, suppose 2 here, and lambda is suppose 2, then 2 times repeated, the chances is there we may get a 0 row, and the chances is also there we may get twice 0 row, right? If it is repeated 3 times, then chances is there we may get a this, either this or this or this. Later on I will discuss for algebraic multiplicity and geometric multiplicity, I will tell you subsequently. But here you note that since the eigenvalue is repeated once, and while we find the eigenvector, we must have one row is 0, one independent row we will get. Okay, so now I adopt the back substitution technique. So let me to solve it. So last row 0 is equal to 0 is fine, the middle row will be mine. So this implies my minus 5x2 plus 5x3 is equal to 0, and this row will give me this, and this row will give me 2x1 minus 4x2 plus 3x3 is equal to 0. If I solve it, your x1 is equal to x3, x1 is equal to x3, is not it? So if I simplify it, I use it here. So that means my 2x1 minus 4, this is x2 is equal to x3, 4x2 and plus it is 3x2 because x2 is x3, okay, is equal to 0. So that means here 2x1 minus x2 is equal to 0. So this implies, what about my x2? x2 is my 2x1, and x1 is independent. Okay, x1 is independent, I say independent. So therefore what happens to my x? My x is x1 x2 x3. x1 is independent, and the value of x2 is 2x1, is not it? And the value of x3 is same as x2, so it is my 2x1. Okay, so if I put x1 is equal to 1, or I may take x1 outside, it is 1 2 2, it is 1 2 2, right? So x1 may be anything. So this is the fundamental one. Therefore x is equal to 1 2 2, or I may write it 1 2 2 transpose to write in a line, is an eigenvector, is an eigenvector corresponding to lambda is equal to 0. And since we choose x1 is 1 here, we may choose anything, right? Anything. So what will get? Thus any scalar multiple and so also any scalar multiple of this of 1 2 2 transpose is an eigenvector, okay? But we stick to this fundamental one, we stick, okay? Now apart from this Gauss elimination method, here we have adopted the Gauss elimination technique. The alternatively another easy technique, I would say, the cross multiplication technique, right? By considering only two equations here. Now you see, from this I write it algebraically, okay? I write it this, let it be my star, right? To make you understand, let it be my star. From star, the alternatively from star, what is my algebraic operations here? Alternative way here, okay? So from star, and we write it directly. If you adopt this method, we can write it directly. It is here 8x1 minus 6x2 plus 2x3 is equal to here 0. The second row will be minus 6x1 plus 7x2 minus 4x3 is equal to 0. And third row will give you 2x1 minus 4x2 plus 3x3 is equal to 0. It is your equation I, it is your equation 2I, it is your equation 3I, okay? And you consider any two. So here I consider I and 2I, okay? And apply cross multiplication. You recall the cross multiplication, recall your higher secondary knowledge, right? Higher secondary knowledge. Here what will we do? We'll do is, you see carefully here, it is x1, I am considering these two, so it is x1 divided by, so remaining 2 row, right? Remaining 2 row I will consider the determinant of minus 6 to 7 and minus 4. That means the x1 divided by this means we are taking this into this minus this into this. And for this middle one, it is always negative. It is minus of x2 divided by, okay? Note that this is always negative, middle one. So x2 divided by this row. Now this row will not consider. We consider this and this. Means it is my 8 2 minus 6 and minus 4. Then while we consider the third, and it is x3 divided by, okay, x3 divided by. So for x3, while we take x3, this will not be considered. We will consider this and this, okay? So it is my 8 minus 6 and minus 6 7, okay? So if you simplify it, it will be my x by 6 4 ja 24 minus 7 2 ja 14 by 10, x1 by 10 is equal to your minus x2 divided by, it is your 20. This minus this is 20, and your x3 divided by, this will be this into this minus this is 20, okay? This into this is 20. Now if you solve it, it is, just a minute, it is actually minus sign, so it is your minus 20, okay? It is your minus 20. You see, these are now proportional, so that means my x1 by 10 is equal to x2 by 20, minus cancel here, is x3 by 20. Since these are proportional, I divide 10 throughout, okay? So I write it x1 by 1 is equal to x2 by 2 is equal to x3 by 3. You see now therefore what is the value of x1 now? So therefore x is my x1, x2, x3. So this will be my 1, x1, this is 1. If I write it, this is equal to some k, or k is equal to some 1, say. In that way, what is the value of x1? x1 is here 1, and x2 value will be 2, and x3 value will be 3. So this is the, sorry, x3, this is 2, so this is 2. So therefore for x is equal to, lambda is equal to 0, x is equal to 1, 2, 2 transpose is an eigenvector, and any scalar multiple of this is also an eigenvector. Okay, so you see this scalar multiplication technique will give you a easy way of getting the result. Okay, we have considered I and 2i. Any two you consider, you may consider 2i, 3i, I, 3i, any two you consider, any two, right? Okay, any two you consider. Okay, similarly for lambda is equal to 3 you can find the eigenvector. For lambda is equal to 15 you will also find the eigenvector. Similarly for lambda is equal to 3, let x is equal to x1, x2, x3 be an eigenvector, and you make it x2 and you make it here x1. Okay, you make it here x1 and you make it here x1, you make it x1, right? You make it x1, let x1. So similarly here you have this such that a minus 3 into I, lambda into I, into x2 is equal to 0, right? So your original one was 8 minus 6, 2 minus 6. So it becomes here, what will happen here with your original? It is here 8 minus 3 minus 6, 2 and minus 6, 7 minus 3 and here minus 4 and it is here 2 minus 4, 3 minus 3, x1, x2, x3 is equal to here 0, 0, 0. Okay, so if you simplify it, so this implies my 2. So if you simplify it, I am writing algebraically, it is my 5x x1 minus 6x2 plus 2x3 is equal to 0. Then here minus 6x1 plus 4x2 minus 4x3 is equal to 0, and here then the last row is here 2x1 minus 4x2 plus 0x3 is equal to 0. Similarly I am considering these two and applying the cross multiplication. Apply cross multiplication to first two equations. We get here x1 divided by, you see, while I take x1, this into this minus this into this, it is 6 4 ja 24 minus 4 2 ja 8 is equal to, middle one will be minus x2, and here I have to consider x2 means this is omitted, this minus 5 4 ja 20, and it is minus plus, second for second we have a minus, and it is minus plus 6 2 ja 12. Then coming to the last one, will be here x3 divided by, we have to see this first two, 5 4 ja 20, right? Minus plus again minus 6 is ja 36. Okay, so this implies my x1 by 16 is equal to minus it is here x2 by 1 minus 8, x2 by 8 is equal to here x3 by minus 16. Okay, so now if you divide by 8, so that means it is x1 by 2 is x2 by 1 is my x3 by minus 2. So the value of x1 is 2, value of x2 is 1 and x3 is minus 3. Therefore here x2 is equal to 2, 1 and minus 3 is an eigenvector. And And similarly, any scalar multiple of this is also an eigenvector for lambda is equal to 3. Likewise, we have to find the eigenvector for lambda is equal to 15. So likewise, for lambda is equal to 15, let x3 be x1, x2, x3 such that this. So this implies what is my a minus 15i in diagonal position we will subtract. It is my 8 minus 15 minus 6 2 minus 6 7 minus 15 minus 4 2 minus 4 3 minus 15. Here x1 x2 x3 is equal to 0 0 and 0, right? If you simplify it, the algebraic equation will be, so if you simplify it, it will give you these three equations. If I consider first two, okay, first two under cross multiplication leads to here x1 divided by this into this minus this into this. So it is 24 plus 16, and middle one I am telling you it is negative, minus x2 divided by, and this is omitted, we have this into this minus this into this, it will be 28 plus 12, and it will be for third one x3, this is omitted, this and this, it will be here 56 minus 36. Okay, so this implies here x1 divided by 40 and here x2 divided by minus 40 is here x3 divided by 20. This minus sign I wrote it here. So dividing by 20, I am getting x1 by 2 is equal to x2 by 2 is equal to x3 by 1. So therefore my x3 is equal to 2, 2 and 1 is an eigenvector corresponding to lambda is equal to 15, and so also any scalar multiple of it, any scalar multiple of this is an eigenvector. Okay, you see the solution to the problem, it seems to be lengthy, but it is if you adopt the cross multiplication technique, then it will not take much time. Okay, so to summarize this problem, you consider the characteristic equation, solve it to find the values, eigenvalues. So as many as eigenvalues, it is same as the order of the given matrix. Okay, here it is a third order matrix, so we get 3 eigenvalues. So the eigenvalues are 0, 3 and 15. Here all are distinct eigenvalues. The cases arises also, the eigenvalues may also repeated. We may have 0, 3 and 3. We may have 3, 3, 3. We may have 0, 3 and 3, 15 and 15. So eigenvalue may be repeated. But here it is a case of distinct eigenvalue. In case of distinct eigenvalue, corresponding to each eigenvalue, we will get a fundamental eigenvector. Okay. Any multiple of the it is also an eigenvector, but this is the dependent with this. So we consider it one, fundamental one. Okay. So as many as eigenvalue, as many as eigenvectors. Once it is distinct, we will get corresponding to each eigenvalue, we will get exactly an eigenvector. Right. Now the moment it is repeated, suppose the eigenvalue lambda is equal to 3 is repeated 3 times. Okay, then the chances are there, we may get one eigenvector, we may get two eigenvectors, and we may get 3 eigenvectors. So as many times as it is repeated, if we are getting equal number of eigenvectors, okay, then it will lead to another beautiful aspect, what is called the defect. There is no defect, because repeated 3 times we are getting 3. If it is repeated 3 times we are getting 2, then the lacking is 1. So defect is equal to 1. Okay, if we are getting one vector, even if it is repeated 3 times, then 2 is lacking, the defect is 2. Okay, and another important aspect we will learn, the diagonalization. The diagonalization is possible only when as many as eigenvalues, as many as eigenvectors. Means even if it is repeated 3 times, we have to get 3. If it is repeated twice, we have to get 2 eigenvectors corresponding to the same eigenvalue. So this is another aspect. So let me to tell you that aspect of repeated case by telling you the algebraic multiplicity and geometric multiplicity. Coming to another important aspects, for a given matrix A, if a particular eigenvalue is repeated m times, then the algebraic multiplicity of that eigenvalue is m. Now, that eigenvalue is repeated m times, but corresponding to that repeated m times eigenvalue, we are suppose getting n independent eigenvectors. Okay. For example, suppose we are getting lambda is equal to 2 to 5. Now for then this algebraic multiplicity of 2 is my 2, right? Is suppose my 3. So now this algebraic multiplicity of 3 is 2. Now corresponding to for lambda is equal to 2, how many vectors we may get? We may get x1, a single vector we may get, or we may get x1, x2 we may get x1 and we may get x2 too, right? So this may happen. So note that always m is here greater than or equal to n, right? As many times. So if we are getting only one we are getting, then here the geometric multiplicity of 3 is equal to here 1. If we are getting 2 here, then the geometric multiplicity of 3 is we are getting 2 here. Okay, we are getting 2 here. So if algebraic multiplicity is equal to geometric multiplicity, then only we can move for diagonalization is possible. So in another important aspect is my diagonalization. So in a later video later lecture I will tell what is diagonalizations, but at this right moment you just note. So as many times the eigenvalue repeated, as many equal number of vectors we are getting, then only diagonalization is possible. Okay, and this difference algebraic multiplicity minus geometric multiplicity, there is another term, short question sometimes being asked, defect. It is algebraic multiplicity minus geometric multiplicity for an eigenvalue, right? This difference is called the defect. So if the defect is 0, diagonalization is possible when this defect is equal to 0. Okay, for the details of this I will tell in diagonalization. The defect is equal to 0. So let us discuss some simple cases. So a question is asked, a matrix A is given and you are asked to find the eigenvalue and eigenvector. Also discuss algebraic multiplicity, geometric multiplicity and defect, and what can you say about its diagonalization, it is possible or not. Okay, so in principle in diagonalization what happen, usually lambda 1 0 0 0 lambda 2 0 0 0 lambda 3, that means this eigenvalue will come in this place, in the diagonal place. Okay, this is what called the diagonalization. It is a 3 cross 3, so I am writing 3 cross 3, and for any order the same can be repeated. Okay, so now coming to the solution here. So consider the characteristic equation. Determinant of a minus lambda I is equal to 0. So that means in diagonal position we just subtract it. 2 minus lambda 1 0 0, 2 minus lambda 1 0 0, 2 minus lambda. You see this sign must be determinant, don't be confused. Okay, don't put any matrix sign, this is 0. Now you see this is a upper triangular matrix. Okay, so this determinant is simply the product of this diagonal. This is product of this because it is a upper triangular matrix. Below it is 0 here. So these are all zeros below the diagonal. So this implies, if I simplify it is 2 minus lambda into 2 minus lambda into 2 minus lambda is equal to 0. If I solve it, so lambda is my 2 2 2. So what is therefore the algebraic multiplicity of 2 is equal to my 3. Okay, now you see eigenvalue is repeated 3 times. So how many eigenvectors we are getting, we'll see now. You see, for lambda is equal to 2, let my x is this is an eigenvector. So then what will happen? A minus 2i into x is equal to 0. So that means here 2 minus 2 1 0 0, 2 minus 2 1 0 0, or 2 minus 2. Okay, matrix, here it is matrix into x1 x2 x3, because we are writing it in system of linear equations form. Okay, so now what will happen? So this is my 0 1 0 0 0 1 and 0 0 0. Okay, it is already in simplified form, is equal to 0 0 0. It is already in simplified form. Nothing can be solved here now. Now it is already in echelon form. You see here non-zero entry is 1, only one single 0 is here. Non-zero entry is 1, single 2 zeros are here. So it is in already in here echelon form. Okay, it is in this. So no further simplification is possible here. So that means how many 0th row we are getting? We are getting is only 1 0 row, right? Only 1 0 row. That means we are getting only one vector here. If we simplify it by back substitution method or usual, it is in Gauss elimination. So now here already it is in simplified form. So your this you multiply it. If you write in algebraic form, your first row give you x2 is equal to 0 and your second row will give you x3 is equal to 0. Okay, right? But what happens to x1? X1 is anything. X1 is arbitrary, right? If you put x1 is anything, then last row will give you, this is 0 into x1 plus it is already 0 and 0. So this will satisfy here. So x1 is arbitrary. So what happens to the eigenvector? Therefore your x is equal to x1 is x1, x2 0, x3 0. So taking x1 out, it is 1 0 0. For putting x1 is 1. So therefore x is equal to, here therefore x is equal to 1 0 0 is an eigenvector corresponding to lambda is equal to here 2, right? This is the only one. Any scalar multiple of this is an eigenvector, okay? But they are LD dependent with original. So we are not counting these are the extra eigenvectors, okay? So this is the only one eigenvector. So you see eigenvalue is repeated 3 times, and from this you can understand that only one vector. If by simplification 2 row will 0, then we will get 2 eigenvector, right? So here what will happen to its geometric multiplicity for lambda is equal to 2 is we are getting is 1 here. Only one vector we are getting. So therefore what is the defect? The defect is algebraic multiplicity minus geometric multiplicity. It is 3 minus 1 is equal to 2, right? So what about your diagonalization? Diagonalization not possible. Why? Now because algebraic multiplicity is not equal to geometric multiplicity. As many as eigenvectors values, we are not getting equal number of eigenvectors. That's why this diagonalization is not possible here. Now coming to 2 other simple examples. Suppose you are asked 2 matrices are given and you are asked to find the eigenvalue and eigenvectors in each case and discuss the defect. Okay, if I think of here A, so what is here? A minus lambda I determinant, is equal to 0, means my 0 minus lambda 1 0 0 minus lambda determinant is equal to 0. So that means my lambda square is equal to 0, means my lambda is into lambda is equal to 0. So I am getting lambda is equal to 0 and 0. You write it, don't write single 0. Okay, so what is the algebraic multiplicity of lambda is equal to 0 is my 2. It is repeated 2 times. Okay, so algebraic multiplicity 2. So what happens to its geometric multiplicity? This is for my eigenvalue. Now for my eigenvector, what will happen? A minus 0i into x is equal to 0 and 0. So that means my in the leading diagonal it will my 0, it is my 1, it is 0 and 0, x1 x2 equal to 0 0. You see it is already in simplified form. No further reduction is possible. So only we are getting only one row is 0 we are getting. So immediately we can declare the geometric multiplicity of lambda is equal to 0 is 1 only, right? 1 only. So what is the defect here? So if at all we want to find the vector here, then what will be the vector here? The first row will give you 0x1 plus x2 is equal to 0. Second row will give you 0x1 plus 0x2 is equal to 0. So the first row will give you So that means my x2 is equal to 0. Now for x2 is equal to 0, x1 is anything. x1 is arbitrary. x1 is arbitrary. So therefore x is equal to x1 and 0. So that is my 1 0. So this is the eigenvector. Okay. So this is the only one eigenvector. Even if this lambda is repeated, 0 is repeated twice, but we are getting only one vector. So therefore, what is the defect? The defect is algebraic multiplicity minus geometric multiplicity. It is 2 minus 1 is equal to 1. Coming to one more example. Coming to the second example, here the for eigenvalue we have this. So that means here lambda square is equal to here 0. Lambda square is equal to 0 means this is 2 means repeated twice. Okay. So lambda is equal to 0 and 0. So therefore algebraic multiplicity for lambda is equal to 0 is my 2. What happens to geometric multiplicity? What happens to my eigenvector? This is my 0 minus 0 0 0 0 minus 0 x1 x2 is equal to 0 0. So what will happen here? So this implies we are getting 0 0 0 0. 2 rows are 0 we are getting, right? We are getting 2 rows are 0. So immediately we can say the geometric multiplicity here is the geometric multiplicity of lambda is equal to 0. We are getting 2 number of zeros row. So is my 2 here. Okay, it's 2 here. So what will happen if you really want to write the vector? 0 x1 plus 0 x2 is equal to 0 means anything. x1 can be anything, x2 can be anything. So therefore x1 and x2 are arbitrary, right? Therefore what happens to the eigenvalue? So putting x1 1 x2 0, what I am getting? I am getting 1 0 as the eigenvector. Again putting x2 1 and x1 0, I am getting 0 1 as the eigenvector. Okay, so these are Li, these are independent. These are independent eigenvectors. If I think of combining them, if I add them 1 0 plus 0 1, this is 1 1. It is also an eigenvector. Okay, but this is dependent. This is also an eigenvector, but this is linearly dependent. Okay, so therefore these two are the independent eigenvectors. Therefore for lambda is equal to 0 0, x is equal to 1 0 and 0 1 are two eigenvectors, two Li independent, linearly independent, okay, eigenvectors. So therefore the geometric multiplicity is 2 here. What is the defect here now? The defect here is algebraic multiplicity minus geometric multiplicity is 2 minus 2 is equal to 0. Now this matrix is ready for the diagonalization is possible. Yes, diagonalization is possible. In other lecture I will tell you what is the diagonalization. Okay, and the diagonalization, the diagonal matrix will be lambda 1 0 0 lambda 2 means we have 0 0 0 0. This is the diagonal matrix here. Okay, so this is all about the algebraic multiplicity, geometric multiplicity and defect. Now come to some important properties of this eigenvalues and eigenvectors. So coming to the properties, as you know, what is the characteristic equation? Characteristic equation is determinant of a minus lambda into I is equal to 0. You know the usual way of solving it, but if you want to solve it in a trick, so what will be this characteristic equation? It will be a lambda cube minus d1 lambda square plus d2 lambda minus d3 is equal to 0. It is for 3 cross 3 matrix. Now in general, if it is a n cross n matrix, then it will be my lambda to the power n minus d1 lambda to the power n minus 1 plus d2 lambda to the power n minus 2, and we go on continue minus plus minus 1 to the power n dn, right? This is equal to 0. This will be my characteristic equation. So this is my characteristic equation. So what is d1? d1 is simply trace of the matrix A, means only the sum of the leading diagonal, and my dn is nothing but it is my determinant of A, and what is my d2? d2 will be my sum of the second order principal minus sum of second order principal minors. So let me to tell you one example for 3 cross 3, then your understanding will clear. Suppose you are asked to find the eigenvalues of this. Okay, so this is the third cross or third order matrix 3 by 3. So what is trace of A? What is trace of A? Trace of A is simply the sum of this. This is 7 plus 1 plus 1 is 9. Now what is your D2? Right, this is your D1. What is your D2? For D2 you see this is a principal minor, means you have to include the diagonal elements, and this is a principal minor. Okay, means second order matrices considering the diagonal elements intact. Okay, then what will be the third order? So we have to consider these two, and for this we have to consider these two. So it will give you the determinant of 7 minus 2, 2 and 1, then plus we have 1, 4, 4 and 1, plus we have 7, 2 minus 2, 1. The determinant we have to add it. So if you solve it, it is 3 minus 15 plus 11 is equal to your minus 1. Now what is your D3? D3 is the determinant of A itself. So if you find this determinant, the determinant will be your 105. So what is A minus lambda I determinant is equal to 0 in one stroke? This will give you, right, this will give you lambda cube minus D1 lambda square, 9 lambda square, plus D2 lambda minus lambda, then it is minus 105. It is your minus 105. So this is your 105 is equal to 0. Okay, alternatively as usual you evaluate the determinant. Okay, otherwise as usual, or what you have to do, as usual you evaluate the determinant, or you directly evaluate, you evaluate 7 minus lambda minus 2 2 minus 2 1 1 minus lambda 4 minus 2 4 1 minus lambda. Okay, directly you evaluate it. Right, you just go on simplify. It will give you lambda cube minus lambda 9 lambda square minus lambda plus 105 equal to 0. Okay, so we may move like this, no issue. Or we may apply properties of the determinant also. You apply properties of determinant, you may apply for if it is a complicated case. To make it simple, you can apply the properties. Okay, property number 2 already I have told you. Property number 2, your sum of the eigenvalue is trace of the matrix. Trace of the matrix means sum of the diagonal elements. Third property also I have told you, it is the product of all the eigenvalue is equal to the determinant of the matrix. Determinant of the matrix means lambda 1 into lambda 2 into lambda n is equal to nothing but a determinant of. Already I have told you. And the fourth property is, if lambda 1 lambda 2 and dot lambda n are values of A, then if something k is multiplied with this matrix here, then k lambda 1 k lambda 2 dot k lambda n, okay, are eigenvalues of k. Right, if a matrix is multiplied by a scalar, then all the eigenvalues are multiplied by this scalar, same scalar. We can make this subbit as suppose this is my A, and subbit B. What will happen to the eigenvalue of A inverse? Okay, what will happen to the eigenvalue of A inverse? If these are the eigenvalue of A, then 1 by lambda 1, 1 by lambda 2, and so on 1 by lambda n are the eigenvalues of A inverse. Lambda I is not equal to 0. Okay, then see what will be the eigenvalues of A to the power p. Right, A to the power p is some positive integer, A to the power p. Then we have here lambda 1 to the power p, lambda 2 to the power p, so on lambda n to the power p are the eigenvalues of A to the power p. And what will happen, suppose here some A minus k, right, suppose some A minus k I make it, then what will happen? The eigenvalues k is a constant here, then it will be my lambda 1 minus k, lambda 2 minus k, and so on lambda and minus k are the eigenvectors. Okay, so these properties are the powerful properties to find the eigenvalues of A inverse, eigenvalues of constant multiple of A, eigenvalues of A to the power v. Okay, for example, suppose you are asked a matrix A is given, you are asked to find the eigenvalues of A. So if you find A minus lambda I determinant is equal to 0, and if you go on solving, you will get lambda is equal to 3, 6 and 9. To check whether it is true or not, what is the summation of lambda I? It is 9 plus 3, 15 plus 3, 18. And what about this sum? This sum is also 18. 6 plus 5, 11 plus 7, 18. So it is correct now. Okay, correctness is there. So what are the eigenvalues of A? 3, 6 and 9. And if I ask what is the eigenvalue of A inverse, since none of them is 0, so 1 by 3, 1 by 6 and 1 by 9 are the eigenvalues. So what is the eigenvalues of A square? It is 3 square, means 9, 36, 81. Okay. If similarly, if it will suppose ask what is the determinant of A? What is the determinant of A? It is simply the multiplication of 3 into 6 into 9. Okay, this is 36 into 9. And this, if it will ask some, what is the eigenvalues of A minus some 3i is asked. What is the eigenvalues of A minus 3i? Okay, A minus some 3i. Then in view of this property A minus ki, so it will simply the eigenvalues will be, right, the eigenvalues will be 3 minus 3, 6 minus 3 and 9 minus 3. Okay, so this is 0, 3 and 3, right? So in this way this property will help you to evaluate the short questions. Okay, so the video is getting lengthy. We should close here. Before closing this video, I must tell you the future aspects. You see, the eigenvalue and eigenvectors, the problems are a little bit lengthy, but I have tried to cover this in a single shot. Okay, so you should learn it carefully, and the preliminary thing is you should have the basic knowledge of your Gauss elimination technique and the basic knowledge of rank, so that you can implement these eigenvalues together. And these properties of these eigenvalues, as I mentioned here, right, and these properties are important for your short questions, so you should learn it carefully. And to practice some other problems, you should go through any standard book and you can practice the problems. Right now, my appeal to you is that if you find this lecture is interesting and such lectures to be uploaded in near future, you should motivate me by subscribing to my channel, Math Tech Insights. Okay, you should subscribe to this channel, Math Tech Insights. Right, this will give me motivation, and as a result I will upload similar videos for you. So in our future studies we will discuss the diagonalization. I have already told the brief of the diagonalization, but the details of the diagonalization I will tell you in the subsequent lecture. So thank you all. We should close the lecture here. Have a good day.